So in today's class, we'll be talking about the design of built-up beams. So you all are aware that what is a built-up beam. A built-up beam is a beam. Suppose you have a general I section, a typical rolled steel I section. And if you want to increase the strength carrying capacity of the same section, what you're going to do is you're going to provide certain plates on the top as well as at the bottom, depending upon the requirement, right? So depending upon the requirement, you are going to place the plates on the top or at the bottom or on the both sides of the flanges. So that kind of section is called as a built up section. So this is one of the cases of where you can use the built up sections. The other case of using built up sections is, suppose if the depth of the beam, okay, if the depth of the beam is restricted. Suppose, say for example, you should not construct or you should not make the depth of the beam more than 500 mm. Okay, so let us consider this example. If the depth of the beam should not exceed 500 mm, then at that time, within 500 mm depth only, you have to make sure the given I section should carry enough amount of load. These are the two possible cases where you can use built-up sections. So the first case is, if you want to additionally make sure to ensure the safety of the member by providing certain kind of plates on the top flange, on the bottom flange, at these conditions, you are going to use built-up sections. That is the first case. Whereas the second case is, if the depth of the beam is restricted. Okay, if in the question or in the real time scenario, if they say, or as an engineer, if someone says to you that you have to design a steel beam, but the depth of the beam should not exceed 500 mm. So at that time also, you're going to ensure the safety of the member by providing the built up sections. Okay, so these are the two possible cases where you can use built up sections. Let us see how to design a built up section when the first case or the second case is given. The design procedure doesn't change, but just the pattern of solving will get changed in one step. Anyways, let's look at this first model problem of design of built up section or built up beams. So the question goes in this way: design a steel beam section for supporting roof of a high wall. It's not high, it's big wall. Okay, please make a correction there. It's a big wall. Roof of a big hall for the following data. So they have very clearly given the clear span is 6.5 meters and the end bearings width is 150 mm and the center to center spacing of beams is 3 meters and the imposed load on the beam is 10 kilonewtons per square meter and dead load, which is inclusive of self weight, is 4 kilonewtons per square meter. And here you can see the restriction on beam depth, right? So if you are designing a beam, the total height of the beam should not exceed 375 mm. So it must be less than 375 mm. That's what the condition says. So the restriction on beam depth, that means you have an I section. Okay, so you have an I section. When you are selecting an I section based on ZPZ value, remember, when you are selecting a section based on ZPZ value, the section should not consist. Suppose, say, for example, you are selecting ISWB. And let's say that you got ZPZ value as some X value. You don't know what exactly this one, some X value. So here you got the ZPZ value as some X value, and you found that in ISWB sections, you have this X ZPZ value at, say, for example, 400. Okay, ISWB 400 represents a ZPZ value which has greater than X. But what is the condition saying? The condition is saying that you should not select the depth of the beam or height of the beam which should not exceed 375 mm. That means, see, here you are selecting ISWB 400, which is satisfying the condition of ZPZ, but you have a condition which said that your beam depth or total height of the beam should not be greater than 375 mm. So at that time, you are not supposed to select this section. Okay, so you are supposed to select any section which has a value less than 375, or which has a depth of less than 375. That means you can go for ISWB 350 or ISWB 300. Likewise, now you have another pattern of solving this problem. Okay, so this is just a rough idea of how to solve this kind of problems. Okay, so when they clearly say, so if you observe the question very clearly, they did not mention anywhere in the question that design a built-up beam, right? So they did not set this one, design a built-up beam. But instead of saying the design of built-up beam, they have given this condition which directly indicates about design of a built-up section or design of a built-up beam. So in the question, there is no compulsory rule that always they will say that design a built-up beam section. No, they don't say in that way. They can come in an indirect way of saying, of asking you to design a built-up beam. So if you find this kind of pattern in the exam, that is the restriction of beam depth or the depth of the beam is restricted to so and so value, then that means it's a built-up beam. How to solve this one, I'll let you know. Okay, so this is the data which they have provided, and here it is also a laterally supported beam. We know we have been talking about two types of beams. One is laterally supported beam and laterally unsupported beams. Okay, laterally supported beam is also called as laterally restrained beam, and laterally unsupported beam is called as laterally unrestrained beam. So we have been talking about only this model of problem since it is limited to your curriculum. So let's solve this problem, the design of built-up beams. So before solving, let's write the given data and then we'll go for the solving process. So given, okay, so the clear span is given, that is L equals to 6.5 meters. Okay, remember here it is a clear span, not the effective span. And they have also given the end bearings width, okay? Or you can make it as width of end bearings. Width of end bearings. So what is the width of end bearings? It is 150 mm. Okay, and imposed load on the beam is also given, which is 10 kilonewtons per square meter. Imposed, remember, imposed load is also called as live load. Imposed load is also called as live load. So don't confuse here. Imposed load on the beam is 10 kilonewtons per square meter. And the dead load is also given, which is inclusive of self weight. Remember, we have solved one problem where they have said that exclusive of self weight, right? In the previous problem, we have solved for exclusive of self weight. At that time, you have assumed certain self weight, that is 1.037, and then you multiplied with factor of safety, and then you have added to the total load, right? So since they have said very clearly that inclusive of self weight, you don't need to assume the self weight of the beam. Okay, remember that condition. So anyways, so and the restriction of beam depth is 375 mm. That is the depth or height of the beam. They both represent the same. The height of the beam should not be greater than 375 mm. This is also one of the conditions which they have specified. Right now, let's find out the solving process. See, here also you're going to find out the bending moment and shear force as the first step, and then the ZPZ value. By using the ZPZ value, you're going to select a section. All these conditions will follow. Okay. Anyways, so let's start with the problem. So the first step, you can keep the heading as the factored loads and effective span. Keep the subheading as factored loads and effective span. Factored loads and effective span. Okay. Why we are specifically calculating for factored loads and effective span? Because they have said only the imposed load. This is not a factored load. Okay, 10 kilonewtons per square meter is not a factored load, and 4 kilonewtons per square meter is also not a factored load. So you have to multiply with 1.5, and then you're going to get the factored dead load and factored imposed load. And again, here they have said that the clear span only is given in the question, that is 6.5 meters. So you have to find out the effective span as well. Okay, so let's come one by one. So let's write the factored imposed load. Factored imposed load equals to 1.5 times of imposed load. What is the imposed load? It is 10 kilonewtons per square meter. So it will be 15 kilonewtons per square meter. Okay. And you also have to calculate for factored dead load. Factored dead load. So which is again a multiplication of 1.5 times of 4, where 4 is the dead load which is given in the question. So this will be 6 kilonewtons per square meter. 6 kilonewtons per square meter. Okay. Now here you have to calculate the effective span of the beam. You have to calculate the effective span of the beam. So how do you calculate the effective span of the beam? So let's find out this one. Effective span. So you know effective span is denoted with L effective or L suffix EFF, where effective span is taken in such a way that clear span, okay, if you remember the concepts of RCC, that is structural engineering 1, you must have calculated the effective span. So clear span plus width of wall. So here they haven't said width of wall, but instead what they have said is width of end bearings. So you can make it as width of bearing divided by 2 plus width of bearing divided by 2. How does this come in? So you have a beam, okay, which is supported on end bearing walls or end bearing supports, and they have set the clear span, not the effective span. So they remember clear span is mentioned, or clear span is the length between inner distances. That is this distance which I have mentioned. So the clear span length is 6.5 meters. Inner to inner distance is called as clear span, whereas center to center distance is called as effective span. So this is the effective span, L effective. So this one we have to find out. So how will you find out this effective span? It can be found out by, you know, the width of end bearing walls, okay, so which is 150 mm. So along this side you have 150 mm width of wall, and along the other side also you have 150 mm end bearing walls. So that's the formula I have written. So width of the end bearing wall divided by 2 plus clear span plus width of end bearing wall divided by 2. Okay, that's how I have written this concept. You must be aware of this thing. Anyways, so L effective equals to, what is the clear span? It is 6.5 meters. So I'm converting into mm, which will be 6,500 plus width of bearing divided by 2. That is this one. Okay, 150. 150 divided by 2 plus width of bearing divided by 2. That is the other side. So therefore 150 divided by 2. So if you solve for this one, you will be getting the answer as 6.65 meters. Okay, this is the effective span of the beam, which is measured from center to center distance of the section. So that's how you're going to calculate the effective span. So now let's find out in the next step the bending moment and shear forces. Bending moment and shear force. So you know the formula for bending moment and shear force for a simply supported beam which is carrying a uniformly distributed load. Okay, so how you are saying that it's an uniformly distributed load? They have very clearly said that 10 kilonewtons per square meter. Okay, when they are mentioning per square meter run, then it means it's a uniformly distributed load. And also they haven't said it's a point load also. Okay, they haven't mentioned it's a point load. So that's the reason why I'm taking it as a uniformly distributed load. So therefore, the maximum bending moment, okay, that is M max, for a simply supported beam carrying UDL is WL square by 8. Okay, this is the maximum bending moment for a simply supported beam carrying uniformly distributed load. Now here, what is this W? Okay, what is this W? W is the weight or the load which is acting on the member. Now, how do you calculate this W? Okay, so this has a separate process of calculating how to find out this one. So here, please concentrate very carefully here. So here you have the factored imposed load as 15 kilonewtons per square meter and a factored dead load as 6 kilonewtons per square meter. Right? You have two factored loads. One is factored imposed load, which is factored live load, and factored dead load, which is 6 kilonewtons per square meter. Now, what is the center to center spacing of the beams? Right? So if you look at the center to center spacing of the beams, it is 3 meters. Okay, remember it is the 3 meters, which is the center to center spacing of the beams. Now, how will you find out the total uniformly distributed load which is acting on the 3 meters span beam? I'll repeat the statement. You have to find, individually the live load and individually the dead load. Now you need the combination of the loads, right? A combination of dead load and live load will be the total uniformly distributed load. Now, if you add just 15 plus 16, okay, that will be 21 kilonewtons per square meter. And remember, this is not the total uniformly distributed load. So you have to find out this 21 kilonewtons per square meter of load is acting throughout a span of 3 meters of beam. Okay, so the length of the beam or the center to center spacing of the beam is 3 meters. So you have to find out on 3 meters length of the beam how much amount of total uniformly distributed load is acting. Okay, I hope the concept is clear. So how will you find out this one? So therefore, total uniformly distributed load, UDL, equals to factored dead load, okay, factored dead load into center to center spacing of the beam, okay, plus factored imposed load or live load, anything is same, factored imposed load into center to center spacing of the beam. This is the process of how to find out the total uniformly distributed load that is acting on the member. So remember this process of solving. So the factored dead load, which is 6 kilonewtons per square meter. So therefore factored dead load is 6 and center to center spacing of the beams is 3 meters and factored imposed load is 15 kilonewtons per square meter. Okay, factored imposed load is 15 kilonewtons per square meter and the center to center spacing is 3 meters. So if you solve for this one, it will be 63 kilonewtons per meter. So this is the amount of UDL load which is acting on the total span of the beam, that is 3 meter span of the beam. Okay, remember, this will be the value of W. 63 kilonewtons per meter is the value of W. Don't add just simply 15 plus 6. That will give you 21 kilonewtons per square meter. That is not the total uniformly distributed load. You have to calculate it for per meter length of the beam. Okay, so in order to calculate what is the uniformly distributed load that is acting per meter length of the beam, this is how you have to solve. Okay, anyways, so let's solve for maximum bending moment, that is M max equals to W L square by 8. So W, that is 63, and L square, where L is the effective span. Remember, don't take it as a clear span, it is the effective span. So it will be 6.65 square divided by 8. Okay, so which will give you 348.25 kilonewton meter. So this is the maximum bending moment. Now you also have to find out the maximum shear force, which is V max. V is called as shear force. So maximum shear force also has to be found out, which the formula, that is WL upon 2, where W is again the total uniformly distributed load acting on the member, that is 63 kilonewtons per meter, and L is 6.65 meters upon 2. Okay, which will be, if you're calculating, it will be 209.47 kilonewtons. So this is the factored bending moment or the maximum bending moment, and the factored shear force, which is also called as maximum shear force. Okay, now in the next step, what you're going to find out is the plastic section modulus required, that is ZPZ value. We'll keep the complete heading as plastic section modulus required. Please keep the heading as plastic section modulus required. Don't just write ZPZ. Okay. Now, how will you calculate ZPZ value? So ZPZ required equals to, you know, the formula which we have been solving in the last two problems, that is M into gamma M naught by Fy. Okay. You know the maximum bending moment, which is M, that is 348.25. So 348.25 into 10 power 6, okay, into gamma M naught value is 1.1 and the value of Fy is 250. So if you solve for this one, you will be getting as 1532.3 into 10 cube mm cube. So this is the ZPZ value required for our section. Now what you have to do is open IS 800 text, open IS 800 code book and find out a section which has a ZPZ value greater than or equals to 1532.3 into 10 cube mm cube. Let's just go for this one initially. So what you have to do is open annexure H of IS 800 2007. Okay, from annexure, please open annexure H of IS 800 2007. So don't remember the condition of depth of the beam is restricted to the 375. Don't go for that one. Just open annexure H of IS 800 2007 and find out a steel section or a steel beam which has a ZPZ value of greater than 1532. And let me know what is that section. So this will be the preference order, that is ISWB will be the first preference and second preference will be for ISMB and third preference will be for ISLB. So you are saying that ISWB 450 is having a ZPZ value greater than 1532. Can you tell me what is the ZPZ value of ISWB 450?
1760.
1760. Okay, fine. 1760 into 10 cube mm cube. Okay. Now, so here, what you have to remember is they have very clearly said that one condition which they have very clearly said is the depth of the beam should not exceed 375 mm. So what is the depth of the beam which you have selected? It is 450 mm. So the condition is not getting satisfied. So you have to select a section which should be less than IS 375. Okay, it should be less than 375. But you have selected a section which is greater than 375, but the value of ZPZ is greater than what is required. That means you need to provide 1532, but you have got 1760. So which is in the safe limits, provided if this condition is not given. Suppose, say for example, if this condition is not given in the question, then you can directly select ISWB 450 and then solve the problem with the process which we have solved. But here they have set a condition that you should not select a section which has a depth greater than 375 mm. So that means you cannot select this section. Okay, even though the ZPZ value is greater than 1532, you should not select this section. It is because the depth of the beam is exceeding 375 mm. 450 is actually greater than 375 mm. So you should not go for this section. Now, how to look for another section? So you have to look for a section which has, now you don't need to worry about 1532 value. What you have to worry about is you have to select a section which has the depth less than 375 mm. So if you refer IS 800, the annexure H of IS 800 2007, you don't find any section with ISWB 375, if I'm right. You'll find the section with ISWB 350 or ISWB 300. You don't find 375 section, right? Am I right? Can someone confirm?
Yes, sir.
Yeah. So you don't find ISWB 375. So since you don't have a section with ISWB 375, you can also not select this one. So the next possible options are either you have to go for ISWB 350 or ISWB 300, right? But however, let's not go for ISWB 300 because you obviously know that both ISWB 350 and 300 will have the value of ZPZ less than 1532. So I'll repeat the statement. If you select ISWB 350 or if you select ISWB 300, both the sections will have the ZPZ value less than the required value, that is 1532.3. But you go for the little greater section, that is ISWB 350. Okay, so you can also say that why cannot we go for ISWB 300? You can select, but what happens is when you are providing the plates, okay, the depth of the plate and the dimensions of the plate has to be increased to satisfy the remaining ZPZ condition. Anyways, I'll get back to that. So now let's select ISWB 350. Okay, so from Annexure H of IS 800 2007, try, I'll write the statement from the beginning. Try ISWB 450, which has ZPZ equals to 1760 into 10 cube cube, right? So this you can select, but the condition is, but as per the condition given in the question, as per the condition given in the question, the depth of the beam, the depth of beam should not exceed 350 mm. 350 mm. Okay, so this is the condition. Therefore, try ISWB 350. Okay, try ISWB 350 at the rate 558.19 Newton per meter. Okay, which has a plastic section modulus of, which has a ZPZ or plastic section modulus, which has a ZPZ of, so if you refer IS 800 2007 Annexure H, the ZPZ value of ISWB 350, okay, is 995.49 into 10 cube cube. Correct me if I am wrong with this value of 995.49. So this will be the value of ZPZ for ISWB 350. But how much ZPZ value you have to provide? You have to provide 1532. But how much you are providing? You are providing just 995. Okay, so you have to provide 1532, but you are providing only 195. Okay, so there is some difference between these values. Okay, so that is 1532. Can you tell what is this value of 1532 minus 995? 1532 minus 995. So it will be 537. Okay, so this is the difference between the provided value and the required value. The required value is 1532, provided value is 995, but you have certain difference of the ZPZ value, that is 537. Now, how will you compensate this difference? How will you compensate this difference? So it can be compensated by providing plates on the top flange as well as on the bottom flange. Remember, you have to compensate this 537 into 10 cube cube difference by providing the cover plates. Okay, by providing the cover plates. That's how the built up section is coming into picture. Okay, so that's, I hope it is clear for all of you. So therefore, section modulus section modulus required by section modulus required by plates. You need to know what is the section modulus required by plate. It is actually 537. Let's make it very clear here. So section modulus required by plates, you can make it as ZA. Okay, just a representation. So section modulus required by plates, ZA equals to ZPZ required, okay, minus ZPZ of provided I section. Okay, so how will you find out this one? It is the ZPZ required value is 1532. Here you can see we have solved this one 1532. Okay, so 1532.3 into 10 cube cube. What is the ZPZ of the I section which you have provided? It is 995.49 into 10 cube. Okay, so the difference of these two values will be the section modulus for plates. So it will be 536.81 into 10 cube cube. So if you are providing plates, you have an I section. Okay, you have an I section. So this I section is having a section modulus of 995.49 into 10 cube cube. Okay, so in order to compensate the remaining plastic section modulus, you are providing the plates on the top flange or on the bottom, and also on the bottom flange. Okay, so this plate is having should have a plastic section modulus of 536.81 both together. Okay, if you are providing two plates, both the plates you should have a plastic section modulus of 536.81 into 10 cube cube. So now you got to know the ZP value or the ZA of the plates, which is 536.81 into 10 cube cube. Now you need to find out what will be the area of the plate. So let's find out area of plate. You can make it as A, capital A, which is area, and small a represents for plate. So how will you find out this area of the plate is? It can be found out as ZA, that is section modulus of plate, divided by total height of the I section which you have selected. Okay, ZA, that is plastic section modulus of plate, divided by total height of the I section. That is how you can calculate the area of plate. So this can be calculated as AA equals to area of the plate, plastic section modulus of plate is 536.81 into 10 cube, and the total height of the section which you have selected is 350. It is ISWB 350. That means the height value is 350. So 350. So which will be 1533.74 square. So this is the area of the plate. Okay. Now you need to find out the width of the plate as well as thickness of the plate. Okay. Now, how will you find out the width of the plate? So take width of the plate or cover plate or flat, anything is same. So take width of the flange cover plate. Okay, so what would be the width of the flange cover plate? It should be equals to, okay, it should be equals to width, flange width of the section, or width of the flange of I section. Width of flange of I section. Okay, remember, if you are providing, see in this diagram I have made with certain difference just to make sure that you are providing the plate. Okay, so but as far as code book is concerned, what does it says is the flange length or the flange width should be equals to the width of the plate which you have selected. Okay, the width of the plate which you have selected. So they both must be same. So that's what I have written here. Take width of the flange cover plate equals to width of flange of I section. What is the width of the flange of I section? So if you refer the steel tables book on the properties of ISWB 300, sorry, ISWB 350, you'll be getting the width of the flange, and the same width of the flange has to be provided as the width of the flange cover plate. Can you tell me what is the width of the flange cover plate? Can you refer 200? Is it 200? Can you tell what is the flange width of I section? That is ISWB 350.
200, sir.
Okay, fine. Thank you. So therefore, the width of flange cover plate will also be 200 mm, which is the width of flange of I section. Okay, so that's how you're going to find out the width of the flange cover plate. Now you need to find out the thickness of the flange cover plate. So let's find out that one. Thickness of flange cover plate. Thickness of the flange cover plate, which you can make it as TFP. They are just representations. That's it. You don't need to bother much about it. So how will you find out the thickness of the flange cover plate? It will be area of plate upon width of the flange. So you know area equals to width into thickness, but you need thickness, so it will be area divided by width. So from that I am writing this one. So therefore thickness of the flange cover plate equals to, what is the area? It is 1533.74. 1533.74, which is the area of the plates. Okay, upon the width of the flange. What is the width of the flange? It is 200. So therefore thickness of the flange plates equals to 7.66 mm. If you solve for this one, you'll be getting 7.66 mm. So therefore you can make the thickness of the flange cover plates as 8 mm approximately. You can also go for 10 mm. That's up to you. Okay, so this will be the dimensions of the cover plates which you have provided. The thickness of the flange cover plate is 8 mm and the width of a flange cover plate is 200 mm. So therefore provide cover plate of size 200 by 8 mm. Okay, so this will be the cover plate dimensions. Now you have to find out what is the ZPZ provided value, right? So far you know the ZPZ required value, right? So the ZPZ required is 1532, but you have provided this ZPZ, that is this 1532 is divided into two parts. One is the ZPZ of the I section and the second one is the ZPZ of the plates. Now you have to add these two things and this will be the value of ZPZ provided. Okay, so ZPZ of I section plus ZPZ of plates will give you the total ZPZ of the section. And remember, this total ZPZ value, that is ZPZ provided value, must be greater than 1532. That's a condition. Okay, so let's find out that one. So ZPZ provided equals to ZPZ of I section plus ZPZ of plates. ZPZ of I section plus ZPZ of plates. You know the ZPZ of the I section, which is 995.49 into 10 cube. Okay, now how will you find out the ZPZ of plates? Okay, you have to find out the ZPZ of plates in this way, that is area of plate, okay, area of the plate into, remember this formula, area of the plate into height of the I section or you can make it this way, area of the plate into height of the I section into thickness of the plate. This is a fixed formula. Okay, area of the plate into height of the I section into thickness of the plate. So this is the formula to find out the ZPZ of plates. So let's look at this value. So 995.49 into 10 cube plus what is the area of the plate? How will you find out the area of the plate? If you multiply width into thickness, that is 200 into 8 will give you the area of the plates. So 200 into 8 into height of the I section is 350. And what is the thickness of the plate? It is 8 mm. So if you solve for this one, you will be getting the ZPZ provided value as 1568.29 into 10 cube mm cube. Okay, so I said here the condition. So the ZPZ of I section and the plates must be greater than 1532. So what is the value which you have got? It is 1568. Okay, so it is greater than 1532 point, what is this value? 1532.3 into 10 cube mm cube. That means it's in a safe condition. So if this condition is satisfying, then only the dimensions of the cover plates which you have provided is safe. Okay, remember this condition must get satisfied. Suppose, say for example, you instead of 1568, just this is an example condition. So instead of 1568, you got the value as 1528, 1528.29 into 10 cube mm cube. Just an example. Okay, and this 1528 is actually less than 1532.3 into 10 cube mm cube, which means it's an unsafe condition. Now what will you do here if the case is unsafe condition? What you have to do is increase the dimensions of the plate. Okay, you can increase either the thickness value or the width value, or you can increase both the values at an appropriate range. Okay, so ensure that the ZPZ provided value must be greater than the ZPZ required value. If the condition is satisfying, then there is no problem. If the condition is not satisfying, then you increase the dimensions of the plate. Don't go for the increase in the value of ZPZ of I section. Don't change any of these I section properties. Keep the I section same. Only parameter which you have to change is the area of the plates, that is the size of the plates, both width and the thickness. So if that is the case, if you get unsafe condition, you can increase the width to 220 mm and you can increase the thickness to 10 mm. So you have to check. That has to be done by you in the exam itself, because it's a trial and error method. Anyways, so that's how you're going to ensure whether the section which you have selected is having the ZPZ value greater than the required value or not. So that's the condition. Okay. Anyways, and here they have also said that the total depth of the section, okay, the total depth of the section should not exceed 375 mm. Now we have to check for this condition also, whether the total depth of the section which you have provided is greater than 375 or less than 375. We have to ensure for that. So let's check that also. So total depth of beam section. Okay, what will be the total depth of the beam section? It is depth of the I section, or the height of the I section, plus 2 times of thickness of plates. Why it is coming? You have the I section, okay, you have the I section, and you know the total depth of the I section, which is h, that is 350 mm. And here you are providing the cover plates, or the plates on the top flange as well as on the bottom flange. Now what is the thickness of the cover plate on the top and the bottom? It is 8 mm. Okay, so therefore the values will be height of the I section is 350, okay, plus 2 times of thickness of plates. It is thickness of the plate on the top and thickness of the plate at the bottom, which is 8 mm. So if you solve for this one, okay, 350 plus 2 times of 8 will give you 366 mm, right? How much should be the depth of the I section? It should not exceed 375 mm. That's what the condition said. The depth of the beam should not exceed 375 mm. So is it exceeding or not? It is not exceeding. So 366 is less than 375 mm. That means we have provided the total depth of the section less than 375 mm. That's what the condition said. So therefore, as far as depth of the section is concerned, it is also the safest section. So that's how the entire process of selecting the section and checking the section whether the ZPZ values and the total depths are in the safe condition or not. From the next step onwards, the process remains same. You have to find out the section classification, and then the check for shear capacity, check for high shear or low shear, and then the check for deflection. These parameters doesn't change. Okay. So please note this correction. It is not HI into TP. It is HI plus TP. Okay. So here it is HI plus TP. I'll write with another color. It is not HI into TP. It is HI plus TP. So earlier I have written it as HI into TP. So please make that correction. So anyways, the answer will remain same. Fine then. So the total depth of the beam section is also solved. Now let's write the sectional properties of ISWB 350. Okay. So the sectional properties of ISWB 350 at the rate 558.19 Newton per meter are. So let's write all the sectional properties. One is the depth of the I section, which is 350 mm, and the width of the flange, which is 200 mm. Please check your steel tables book. You will get all these properties. So thickness of the flange equals to 11.4 mm, and thickness of web equals to 8 mm. The radius at root R1 equals to 12 mm, and the moment of inertia along ZZ axis equals to 15521.7 into 10 power 4 mm power 4, and the ZPZ value, which is plastic section modulus, is 995.49 into 10 cube mm cube, and also ZEZ value, which is the elastic section modulus, which will be 887 into 10 cube mm cube. So these are the sectional properties of the ISWB 350. Okay, so now let's solve for the next step, that is the fourth step. So the fourth step is section classification or classification of section. So from here on, you just try to solve on your own. I'll solve it, but please try solving on your own also. The same process. So how will you find out? So it will be B by TF. This condition has to be followed, which must be less than 9.4 epsilon. And you have to find out another section, which is D by TW, which must be less than 84 epsilon. And remember, the epsilon value is 1. You know the formula, right? So this is obtaining from table 2 of IS 800 2007. So I don't write the Codal book values again and again. You can refer the previous problem. Anyways, so B value is taken as B equals to half of the width of the flange. That is, width of the flange is 200 upon 2, which will be 100 mm. Okay, so therefore B by TF equals to 100 divided by the thickness of the flange is 11.4, which is 8.77, which is less than 9.4. Okay, and you have another condition, which is D by TW. Now how will you calculate the D value? It is the height of the I section minus 2 times of thickness of the flange minus 2 times of radius at root. So which will be D equals to height of the I section is 350 minus 2 times of thickness of the flange is 11.4 minus 2 times of radius at root is what is radius at root? That is R1 value. Sorry. R1 value is 12. Okay. Minus 2 times of 12. So therefore, if you solve, the value of D is obtained as 303.2 mm. Okay. So therefore, D by TW equals to 303.2 divided by TW is the thickness of the web, which is 8 mm. So therefore, this value is obtained as 37.9, which is again less than 84. So since D by TW is less than 99.4 and D by TW is less than 84, the section is plastic. Okay. Why? How you are telling the section is plastic? It is because the value of B by TF is less than 9.4 epsilon and D by TW is also less than 84 epsilon. Okay. Anyways, so this is how the section is classified. And the next step is check for shear capacity. Check for shear capacity. How do you check for shear capacity? Okay, it is checked as design shear strength of section. Okay, you know the formula, that is VD value. So design shear strength of section. So you know the formula, but that is VD equals to Fy upon root 3 into gamma m naught into H into TW. Okay, so therefore VD equals to Fy value is 250 upon root 3 into gamma m naught is 1.1 into height of the section is 350 and the thickness of the web is 8. So if you solve for this one, you will be getting in kilonewtons as 367.4 kilonewtons. And you also have to find out the value of check for low shear case or high shear case. And here remember the value of VD. Okay, the value of VD is greater than V. What is V? It is the shear force which you have calculated in here, 209.47 in the second step. So 209.47 kilonewtons. So this condition is safe. So now you have to check for high shear or low shear case. So that means you have to solve for 0.6 VD equals to, therefore 0.6 VD equals to 0.6 times of VD, that is 367.4. I hope you are all aware of this calculation. So I'm going a little fast. I hope you are all getting with the pace of the problem. So this will be 220.4 kilonewtons. Okay. So here 0.6 VD is greater than V, capital V. Okay. Or you can make it as V is less than 0.6 VD. Okay. Since V is less than 0.6 VD, you know the condition, which is for low shear case. So if V is less than 0.6 VD, it is low shear case. Low shear case. So when it is for low shear case, the next step has to be solved for check for design bending strength. Check for design bending strength. So how do you solve for design bending strength when it is for low shear case? You know the formula, that is MD equals to beta B into ZPZ into Fy by gamma m naught. So what is beta B value? If it is a plastic section, the value of beta B is 1. And here, what is the ZPZ value? Here, the ZPZ value is the ZPZ of I section and the ZPZ of the plates, the combination of these two. Okay, so this one you have to take, that is 1568.29. This value has to be taken. Remember, don't directly take the value of ZPZ of I section. It is not just I section. You also have plates for the section. Okay, so therefore the value of ZPZ is 1568.29. 1 into 1568.29 into 10 cube into Fi value is 250 upon gamma m naught is 1.1. Okay, so if you solve for this one, you will be getting the answer as 356.43 kilonewton meter. Okay, and here the value of md is greater than m. What is the m value? It is the maximum bending moment. If you check down, the maximum bending moment is 348.25 kilonewtons. So since md is greater than m, it is also in safe condition. Okay. Anyways, yeah, fine. So now here md should also be less than, okay, if it is a simply supported beam, the value of md should also be less than or equals to, this condition is also there, 1.2 into ze by gamma m naught. Okay, remember this condition we have solved. So I'll just go through the previous problem and I'll show you how have we solved this one. Okay, so yeah, here you can see 1.2 into ze into fi by gamma m naught. Whatever the md value you have calculated here, it must be less than this value also. So let's also write that value. So 1.2 into ze into fi by gamma m naught. Okay, here it is fi. 1.2 into ze into fi by gamma m naught. So you check for this condition. However, it will be in the safe limits only. There is no issues. Okay, you can check for this one and it will be in safe only. So since it is in, it will be in safe condition, I'm not checking it again and again, but still you can give it a try. Okay, so the next step for deflection. So check for deflection. Check for deflection. Now, how will you find out the check for deflection condition? So you know the maximum deflection value, okay, delta max equals to, it's a simply supported beam carrying UDL load. What is the formula for maximum deflection? It is 5 by 384 into WL power 4 by EI. Okay, 5 by 384 into WL power 4 by EI. So you know all the values. Okay, but here the value of W has to be focused very carefully. So which value of W has to be taken now? That's the key thing. So here, if you check down, the value of W is the summation of the total dead load and the total live load, which is 63 kilonewtons. Okay, so here 63 kilonewtons per meter, which is the total UDL load. So remember, in built up sections, okay, the condition of W, that is 63 kilonewtons per meter, should not be taken directly. Okay, in built up sections, remember this thing. So in built up sections, what you have to take is, this is the factored dead load, or the factored, not dead load, it is the factored uniformly distributed load. But what you have to provide is the working load. So W should be the working load here in built up sections. So remember this condition, W should be the working load. I'll write it here. W is working load. You have the factored load. Okay, what is the factored load? It is 63 kilonewtons. So in order to find out the working load, how will you find out? It is the factored load upon 1.5, right? This formula is coming from, you know, you have to find out factored load equals to working load into 1.5. That is factor of safety. So from this, you are just cross multiplying and finding out the value of working load. So therefore, factored load equals to, what is the factored load value? It is 63 kilonewtons per meter. Okay, and divided by 1.5, which will be 42 kilonewtons per meter. Remember, this should be the value of W. When you are finding out delta max, the value of W has to be very carefully checked. Don't directly take it as 63. it must be divided by 1.5 in order to make it as a service load or the working load. Okay, so that must be clear for all of you. So it will be delta max equals to 5 by 384 into W, which is 42 into L. Here, remember, L is the effective span. Don't take it as the clear span distance. The clear span distance is, sorry, let me go through this. So here you have two spans. One is the effective span is 6.65 meters and the cleared span is 6.5 meters. Okay, so the effective span is 6.65 meters and the cleared span is 6.5 meters. It is not the effective span which you have to consider, it is the clear span which you have to consider in the design of built-up sections. Remember, in the design of built-up sections, you have to consider the clear span, not the effective span. I made a mistake while telling that it must be the effective span. It must not be the effective span. It should be the clear span, which will be 6,500. Okay, power 4 upon the Young's modulus value is taken as 2 into 10 power 5 into IZZ. Okay, IZZ of the, it is not just the IZZ of the I section alone. It should be the IZZ of the plates and also IZZ of the I section. Okay, so you must know that I value provided. Have you solved for that one? One, okay, we haven't solved for moment of inertia of both the things. Anyways, I'll just solve it here. IZZ total. Okay, please make this one also. IZZ total equals to IZZ of I section plus IZZ of plates. So we had to solve for this in the previous step only. I forgot this one. Anyways, let's solve for this one. So how will you find, I mean, you must have an idea about IZZ of I section with IZZ of plates finding out pattern. Okay, so can you solve and let me know what is the value of total moment of inertia of the entire I section, that is the built up section. I'll just try to solve. Let me know the answer because I haven't solved for this one. That is IZZ of the I section is 15521.7 into 10 power 4. And how will you find out IZZ of the plates? You have two plates, so I'm multiplying with 2 into BD cube by 12. Okay, that is width of the plate into thickness of the plate cube divided by 12. Okay, plus area of the plate, that is 200 into 8. Okay, into y bar, that is total, no, sorry, it is not y bar, yeah, y bar square, however. So it will be height of the I section plus thickness of the plate divided by 2 whole square. Okay, this is how you can find out the value of IZZ of the plate. So I'll write the clear statements here. So it is the BD cube by 12, and this is the area of the plate, and this is the y bar square. Okay, how does this y bar is coming? It is coming as, I'll just write out this one. Okay, so you have the plates as well. You also have the plates. Now y bar is the distance from extreme top fiber or extreme bottom fiber, from extreme top fiber to center of the section. Okay, so you can find out this. The total height of the section is 350. That is 350 divided by 2 plus 8. That is the thickness of the plate divided by 2. It is not from the extreme top, it is from center. Good. And I hope you know how to find out the value of y bar. So anyways, this is how you can find out the IZZ value of the total built up section. So this will be 2577 6.52 into 10 power 4 mm power 4. So if there is any mistake in this calculation, let me know. Okay. So anyways, so here in calculation of delta max, the value of I is taken as 25776.52 into 10 power 4. So if you solve for this one, okay, the value of delta max is obtained as 21.10 mm. Okay, 21.10 mm. So now what is the permissible deflection value? So this you can write down separately, or just make sure you are calculating the value of IZZ. Now, what is the condition for check for deflection? The delta max value must be less than the permissible deflection. What is the permissible deflection? Delta equals to L by 300. Okay. What is L? It is the clear span. That is 6,500 divided by 300, which will be 21.66 mm. So here the value of delta max is less than delta. Therefore, safe in deflection. So the value of delta max is safe in, since delta max is less than delta, it is safe in deflection. So here, let's also find out the last step, which is check for web bearing. So the 8th step, you can make it as check for web bearing. So how will you find out the check for a web bearing? You know the formula, that is bearing strength or force in web, that is FW equals to, okay, you know this formula, that is B plus N1 into TW into Fy by gamma m naught, Fy upon gamma m naught. Now here you don't know the value of B, right? If you compare with the previous problem, in the previous problem they have said assume, they have said the stiff bearing length, but here they haven't said the stiff bearing length. But I have said one condition there, the stiff bearing length should range between 75 to 100 mm. Okay, remember this condition, the stiff bearing length, that is B. So therefore assume stiff bearing length B equals to 100 mm. You can take any value between 75 to 100, that's up to you, but I'm just taking the extreme value, that is 100 mm. Now how will you find out the value of N1? N1 equals to 2.5 times of thickness of the flange plus radius at root, that is R1. So that will be 2.5 times of the thickness of the flange is 11.4 and the radius at root is 12. So if you solve for this one, the value of N1 will be 58.5 mm. So therefore, force in web or the bearing strength FW equals to B value, we have assumed it as 100, and N1 value is obtained as 58.5 into TW, that is the thickness of the web. Okay, so the thickness of the web is 8, okay, into Fy, which is 250, and gamma m naught is 1.1. And if you solve for this one, will be 288.18 kilonewtons. Okay, it will be 288.18 kilonewtons. So this is how you can find out the value of Fw. And remember this value of Fw, okay, we know the condition. The value of Fw must be less than V, which is the maximum shear force, right? What is the value of V? It is 209.47. So it is 209.47, which is greater than the value of Fw. So therefore, the web bearing is also in safe condition. So this is the entire process of a design of the built-up section. The only parameter which is getting changed is calculation of ZPZ and checking for the depth of the section and I value, that is moment of inertia. I'll just give a summary note of whatever we have solved so far. So just for your understanding, I'm making the summary note. So what we solved initially is, so forget about the effective span and the maximum bending moment and shear forces. So initially you have found out the effective span. Since effective span is not given, if effective span was given in the question, you don't need to actually solve for this effective span condition. Anyways, the effective span we have found out, and then the bending moments and shear forces are found out. And in the next step, we have found out the value of ZPZ. So based on the depth restriction, okay, based on depth restriction. So you have certain amount of depth which was restricted for you, and based on this, you have selected the ZPZ value, and then you have selected a section. And in the next case, what you have done was you have found out the ZPZ of plates, okay, and then you have found out the dimensions of the plates, that is width and thickness of the plates. So the width of the plate is taken as the width of the flange, and thickness of the plate you have found out by calculation. And then the ZPZ provided value has been found out. Okay, the ZPZ provided value, and ensure that the ZPZ provided must be greater than the ZPZ required, which you have calculated in step 2. I mean, as far as this condition is concerned, okay, in step 2. So if it is greater than ZPZ required value, then you have considered that section, and then you have solved it for the next steps, that is section classification, and then you have found out for shear strength values, so section classification, then you have found out the shear strength capacities or the shear strength parameters, and then you have found out whether it is a low shear or high shear case. Okay, so after finding out low shear or high shear case, you have found out the value of MD, that is design bending moment or design bending strength, and then you have found out the value of I. Okay, the total value of you can make it as moment of inertia of I section and plates. Okay, and in the last but one step, we have found out for the deflection value, check for deflection value, and then you have found out the check for web bearing. Okay, so this is the entire process which we have solved so far. Okay, so this is the process of designing a built-up beam. Okay, this is the total process of solving the design of built-up beam.